Hi everyone, I'm here to talk to you about Platonic solids today. So just to start, Platonic solids are convex, regular polyhedra. Does anyone have any idea what convex might mean in terms of polyhedron? Anyone have any ideas? No? Right, okay. So a convex polyhedron is a polyhedron where if you connect any 2 points on its surface together, then it lies entirely inside the polyhedron. I'll give you some examples here. So if you look at the cube, if you draw a line between any 2 points on its surface, for example, let's say there, and from this space here, you can see that the line that joins these two will be behind this orange line here inside the cube. So the cube is convex because no matter where the 2 points are on the surface, you always get a line on the surface or inside the cube. But can anyone see why this one here wouldn't be convex? Yeah? Does anyone have a go and draw a line? That's the line's outside? Oh.
So maybe just draw from here, there, and then to there, right there.
Yeah.
If you draw a line through there, it would, this part would be outside, right there.
Right, yeah. That's great, thanks. So that's what convex means. And regular is a little bit more obvious. So all the faces of the polyhedron have to be regular polygons, and they all have to be the same size, congruent. Okay. Right. So these are the 5 Platonic solids. Does anyone have a go at naming them? Yeah.
Is one of them a cube?
Yeah, why not? This one here, that's the cube. Anyone else? Anyone else have got any ideas? Or any other?
Tetrahedron.
Yeah. This one here is tetrahedron. Any others? Yeah.
Is one of them a dodecahedron? Or
Yeah. Do you know which one?
it's the one at the far right.
This
One
one?
at the very, yeah.
Not quite. That's this one here is an icosahedron. Close. The dodecahedron is this one here. And does anyone know what the one in the middle is called? No? Okay, the one in the middle here is an octahedron. That might yeah? Octahedron. And those are the only 5. And we can show that these are the only 5 Platonic solids on the next slide. We can see that these Platonic solids are made of triangles here, squares and pentagons. So if we look first at triangular Platonic solids, so these ones here, you can see that the tetrahedron, you can see about 1, 2, 3 meet at each vertex, right? But the octahedron, there's 1, 2, 3, 4, and the icosahedron, there's 5 at each vertex, right? So we can see 3, 4, 5. These form each of the vertices. So if you imagine folding this inwards like that, you can see that forms this part here of the icosahedron. And this here, if you fold that inwards, you can see you get one of the vertices of an octahedron, and the same for a tetrahedron here. Can you all see how if you fold, let's say, this edge here and this edge here, if you fold them together, then you get some sort of shape like that, and that's what you see around here. Do you see? So that's great. We've got a tetrahedron, octahedron, icosahedron, but if we try and add a 6th triangle, you don't get a Platonic solid. And does anyone know? Can anyone explain why we can't have 6 triangles at a vertex? Yeah.
Isn't it because you'd be unable to fold it in a way that you could create a closed object?
Right, yeah, because this is, if you just imagine this, it's just like a flat piece of paper, you can't really fold it along any of the lines, so you wouldn't get a Platonic solid there. And you can say the same for squares. So you can see 3 squares around the point give you your cube, 1, 2, 3. And if you try and add a 4th, then you can see it's the same as with the triangles, you get just a flat piece of paper. The pentagons is a little bit easier to see perhaps why you can't have four pentagons around the point. They just wouldn't fit, it kind of look like that. It would overlap and you can't fold that either. And hexagons, 3, they won't fit together, same as the 6 triangles. Okay, and here's just a table summarising each of the 5 Platonic solids, the number of polygons at each of its vertices, and the total of the angles at each of the vertices. And you have to see this has to be less than 360, otherwise you would get overlap. So you can use Platonic solids in many areas, especially in science. So these are some crystals that are formed during ionic bonding, and you can see how they kind of link to the Platonic solids. They've got a very geometric shape. And then allotropes of carbon, you probably did those in chemistry. So they've got, you can see, pentagons and hexagons. So these are actually called Archimedean solids, I think. I think that's how you pronounce it. And they're made of regular polygons, but they don't all have to be the same. So you can see you've got a mixture of hexagons and pentagons there. Okay, right. Now we can move on to Euler's formula. And Euler's formula says that for any convex polyhedron, that V minus E plus F equals 2. And where V is the number of vertices, E the number of edges, and F is the number of faces. And we can show that for a few examples. So for the first one here, show that a cube satisfies Euler's formula. So can anyone tell me how many vertices, edges, and faces a cube has?
Does it have 6 faces?
Yeah, 6 faces. Do you know how many edges and vertices are?
8 verses.
Yeah. And how many edges? Yeah.
12.
12. You've got 4 at the front, 4 at the back, and then 4 connecting the 2 front and back faces. Okay, and now if we try and plug that into Euler's formula, you get 8 minus 12 plus 6, and that gets 2, as we expected. And we can do the same for an octahedron. So this one's slightly harder to count number of vertices, edges, and faces, but you can see there are 1, 2, 3, 4 faces on top, 4 faces on the bottom. There are 8 faces. So 8 faces. There are, I think there's 12 edges, and then there's 6 vertices. So 6 minus 12 plus 8 will give you 2. Does anyone notice anything about the number of vertices, edges, and faces in the cube and the octahedron? So if you remember the cube, so the cube had 8 vertices, 12 edges, and 6 faces, and the octahedron had 6 vertices, 12 edges, and 8 faces. Does anyone notice anything?
It's all even.
Yeah, they're all even. That's one thing. Anything else? Anything else you notice about this?
Yeah. The numbers are like reversed.
Right, so you can see the number of edges are the same, but the number of vertices of the cube and faces of the octahedron are swapped around, and so have the number of faces. And that's not a coincidence. That's the same for the dodecahedron and icosahedron as well. So the dodecahedron has 20 vertices, 30 edges, and 12 faces, and the icosahedron has 12 vertices, 30 edges, and 20 faces. And we can have a look at why using this diagram here. So if you notice, if you take the midpoints of each of the faces of the cube and connect them together, you get an octahedron. So each of the faces have become a vertex of its dual Platonic solid. So if there are 6 faces in the cube, if you take the midpoint as a vertex, there'll be 6 vertices for the octahedron, and the same for the cube and the octahedron here. So the octahedron has 8 faces, and if you turn each of them into a vertex, you get 8 vertices. That gives you your cube. And the tetrahedron is self-inverse because it has 4 faces and 4 vertices. So if you swap them around, you just get 4 vertices and 4 faces again. So that's why there's only 5 and not 6 Platonic solids. So we can apply Euler's formula in graph theory very often. So have any of you heard of graph theory before? Yeah. So that's just talking about nodes and their connections, right? I think, do you do decision maths?
Yeah, we just did this actually.
Right. So I'm sure you'll be experts at this, right? So Euler's formula can be used to check whether or not a graph is planar, and that just means that you can draw a graph with no intersecting edges. We'll get onto that more in a minute. So as you can see, designing computer chips, you need to make sure there's as little intersection as possible, and this will help with that. And a little more obviously, you can use Euler's formula to check that certain numbers of vertices, edges, and faces will not give a polyhedron, convex polyhedron, because v minus e plus f will not equal to. Okay, right. Now this is the interesting bit. How do we prove Euler's formula? So before we do that, one thing we need to use is that we can represent 3D polyhedra using graphs. So here is the example of the graph for a cube. So as you can see, each of the 8 vertices of the cube are turned into vertices of the graph, and each of its edges are essentially the same, just connecting each of the vertices. But now we're in a 2D shape here. And each of the regions of the graph, you can think of them as faces. But there is one face missing, right? The front face. So usually when we talk about these graphs like this, we'll say that the outside region is also a face, and we can call that the front face. And Steinnitz's theorem states that for all convex polyhedra, you can form a connected planar graph like this. So that just means that all the vertices are connected, and you can draw the graphs without any of the edges intersecting. So, does anyone have a go at drawing the planar graph of a tetrahedron? Anyone have a go?
I'll have a go.
Yeah.
Oh, no, I see it.
Perfect, thanks. So you can see you've got the 4 vertices and they're all connected to each other. You can kind of see the triangular shape. So 4 vertices, I think you go. The 4 vertices, and you've got the 1, 2, 3, 4, 5, 6 edges here. Okay. Now one slightly harder planar graph to draw is the octahedron. Does anyone have a go at this one? Yeah?
I don't see it.
This one's slightly harder. You want to have a go? You might want to start by drawing this bit here. This square in the middle, that might be.
Yeah. I'm sorry. I can't even imagine it. Actually,
does anyone else want to have a go? Anyone have a go? almost there, but you put 8 vertices. I think you put too many. Almost, you're almost there. So this graph would look something like this. So you would have the middle section here, and then if you, it might be easy to see if I change colour. For this top bit up here, you could say so this represents that vertex here. So you need to have this vertex connecting each of the 4 middle ones. So like that. The lines don't have to be straight, but this blue bit represents the blue bit on the tetrahedron, and if we're going to do the same for the bottom bit, if we want our graph to be planar, then we can't put it down here, because then connecting to these here we'll have to cross. So instead we can put our vertex in the middle here, so that we can connect it. We can connect it like that, and that's our planar graph. So that green bit's done there. So that's what our planar graph for an octahedron would look like. Okay. So one more thing we need to quickly look at is the angle defect at a vertex of a polyhedron is equal to 2 pi minus the sum of the angles at the vertex. Have you guys met radians yet? Radians? No? Yeah? I'll quickly go through it. So a radian is essentially another way of measuring angles. So if we have a circle like this, not really a circle, but that's fine. If we draw a sector like this, so that this arc length is also the same length as the radius, then this angle here will always be 1 radian. And so that means because the circumference of a circle is 2 pi r, there are 2 pi radians in one whole rotation, or 360 degrees. So, just to go over that again, if we take a sector with arc length r, that will give us the angle 1 radian. And because if we want to know what the whole rotation is 360 degrees, we know that the circumference of the circle is 2 pi r. So if we draw another sector, this is another radian, and so on until we go all the way around, we know we'll get 2 pi lots of these sections, right? So there will be 2 pi radians in a full circle, or 360 degrees. And that gives us our conversion between degrees and radians, and mostly in calculus it's a lot easier to work with radians than degrees. It just gives nicer numbers. So that's what we'll be using today. Don't worry too much if you don't get that. It's just another way of measuring angles. And so the total angle defect of a polyhedron is the sum of the angle defects at each of its vertices. We'll go over what that means on the next slide here. So if we want to find the total angle defect of a tetrahedron, then the first step is to find the angle defect at each of the vertices. So for example, if we look at this vertex here, the total angle defect is equal to 2 pi, or 360 degrees, minus the sum of the angles at that vertex. So if we see here that we've got 3 triangles here, and each angle in a triangle is 60 degrees, right? We'll just forget about radians for now, we'll just carry on with degrees. So if there are 3 triangles with each angle 60 degrees at a vertex, then can anyone tell me what the sum of the angles at the vertex would be? Yeah? 180. So the total angle defect is 360, that's equal to 2 pi radians. 360 minus 3 times 60, right? 180. And that also equals 180. So that is the total angle defect at one vertex of a tetrahedron. And if you want to find the total angle defect, that's just the angle defect at each of its vertices. And we know there's 4 vertices, so we times that by 4. So the total angle defect is equal to 180 times the 4 vertices. That should give us 720. And if we do the same for a cube, each of the vertices has 3 squares around it, and each square has an angle of 90 degrees in each of its corners. So 90 plus 90 plus 90 is 270. So the angle defect at the vertex of a cube is 360 minus 270, and that equals 90. But there are 8 vertices in a cube, so we can see that the total angle defect is 8 times 90, and that is 720 again. And that's not a coincidence that we get the same number. It turns out that for all convex polyhedrons, we get 720 as its total angle defect, and we'll have a look at that later on as well. Okay, so there are many different proofs of Euler's formula. We're going to look at 2 today, and you can find 19 more on this website here. So if you just type in 21 proofs of Euler's formula, you can have a look at that if you want to. It's quite interesting. Lots of them are very complicated, so I took the 2 most, well, easiest to understand. Loads of them were, I don't know what that is. I don't know what that is, but if you want to, you can have a look at some more proofs. The 2 that we're going to look at today involve graph theory and angles. So the first one we're going to look at is a proof by induction. Have you done proof by induction before? Okay, so if I just write down this board. So a proof by induction is one of the different types of proofs you can do. Other ones are like proof by exhaustion, so if you try all the different possibilities, you can show that something's true. Or proof by counterexample, so if you find an example that doesn't work, then you know that that thing isn't true. But a proof by induction, you start off by saying, by proving something is true for a base case. So, for example, n equals 1. So that just means that you prove something true for its first case. So if the example of proof was prove that n equals 2n minus n, that's quite simple. We can use that as an example here. So if we prove true for n equals 1, if we put n equals 1 to here, you get 1 equals 2 minus 1, which equals 1, so that's alright. And our next step is to assume something the statement is true for n equals some value, and we'll call that k here. So then that means we can assume that k equals 2k minus k. And then our next step is to prove true for n equals k plus 1. And if we plug n equals k plus 1 into here, we get k plus 1 equals 2k plus 1 minus k plus 1. And if we prove this is true, then we know it's true for n equals 1, we've assumed it's true for n equals k, we know it's true for n equals k plus 1. So, if we know it's true for n equals 1, so if we know it's true for n equals 1, then because we know if it's true for n equals k, then it's true for n equals k plus 1. If it's true for n equals 1, then it will be true for n equals 1 plus 1, which is n equals 2. And if it's true for n equals 2, then it's true for n equals 2 plus 1, which is n equals 3. And then you've shown that something's true for all n, right? So that's how proof by induction works. In this case, we'll be looking at the edges of the graph. Okay. Okay. So we're going to start this proof. So our base case, this is the n equals 1 case. So we're going to prove that Euler's formula is true for a graph with no edges. Graph with no edges. So what would a graph with no edges look like? What do you think? A connected graph with no edges.
It could just be a point.
Yeah, just a point. We can't have 2 points because then this graph wouldn't be connected anymore. So a graph with no edges would just be a graph with 1 point. Alright. Can anyone tell me how many vertices, edges, and faces this graph would have? Yeah?
So 1 vertices,
Yeah, 1.
no edges.
No edges. And faces. Remember the faces is the same as how many regions there are. So how many regions would you say there are?
Regions. 0.
You could count the whole outside region as well,
Oh, yeah.
basically. So you've got one face. So if we plug that into Euler's formula, V minus E plus F, you get 2. So we proved that Euler's formula is true for our base case, so a graph with no edges. And once we've done that, we need to assume that it's true for some k. So if we assume that Euler's formula holds for a graph with, let's say, e edges. Okay, so now we've proved that it's true for no edges. We've assumed that it will hold for a graph with e edges, and our next step is to prove that it holds for a graph with e plus 1 edges. Right? So, cool. So this is equivalent to saying a graph with e minus 1 edges. It doesn't really matter what we choose, what we assume to be true. But if we choose to assume that it holds true for a graph with e minus 1 edges, then it just makes it easier when we follow our inductive step for a graph with e edges. So to prove that a graph with e edges follows Euler's formula, we can look at 2 cases. So G is acyclic and G is cyclic. Have you looked at these terms in decision yet? No? So acyclic means that in the graph there's no loops. So for example, this would be an acyclic graph because there's no cycles. And an example of a cyclic graph would look something like this because there's a cycle back, full loop. So if we look at first if G is acyclic, so that means that G would look something like this. There's no cycles, and we call this sort of graph a tree. So there are no loops anywhere, and this tree has 5 edges and 6 vertices. And one thing that's always true about the tree is that there's always one less edge than there are vertices. So if we were to start with just 1 point, then there is 1 vertex and no edges. If we were to add an edge to this, we need to add 1 vertex and 1 edge. So now there's 2 vertices and 1 edge. If we add 1 more, then there will be 3 vertices and 2 edges. So you can see as you keep adding more and more branches to the tree, there will always be 1 less edge than there is vertices. So, can anyone form an equation for me then, in terms of edges and vertices for acyclic graphs?
V equals E plus 1.
V equals E plus 1. Because the number of vertices are always equal to the number of edges plus 1 in an acyclic graph. So, if we plug this into Euler's formula now, so V minus E plus F. Here, how many faces would there be in an acyclic graph, or regions? 1, yeah. So 1, so F equals 1. So V equals E plus 1. We can keep E the same. And then F is always equal to 1. So E plus 1 minus E plus 1 is equal to 2, right? So we can show that V minus E plus F is always equal to 2 for acyclic graphs. And for cyclic graphs, so this is a graph where there is a cycle. So it would look something like this. So if we were to remove an edge which is part of a cycle, then there would be, so the number of edges would be equal to the number of edges before minus 1, because we've taken one edge away, right? So if we were to take this edge away, then the number of edges would be 1 less. The number of faces would also be 1 less. Can anyone tell me why there would be 1 less face? If we remove an edge that's part of the cycle?
Wouldn't it join two faces together?
Right, so this would be another region normally, but then if we remove that edge, we've taken away this face, and that becomes part of another face. That's also true for a graph like this. So if we take this edge here, which is part of 2 separate faces, if we take that off, then we still get 1 less face, because the 2 faces have turned into 1. So whenever we remove an edge that is part of a circle, there will always be 1 less face and 1 less edge, and the number of vertices stays the same, right? So if we look at V minus E plus F again, so V is the same. E is now E minus 1, and F is now F minus 1. Sorry, it's a bit messy. So this is equal to V, not so number of vertices stays the same, number of edges, there's 1 less edge and there's also 1 less space. So put that into V equals V minus E plus F. We would get V minus E minus 1 is the same as minus E plus 1, and plus F is plus F minus 1. And here you can see that the 1s will cancel, so we get, so if we call this Euler's formula, if we're trying to find what Euler's formula is here, so Euler's formula is equal to V minus E plus F, V minus E plus F. And because we've assumed that the Euler's formula holds for all graphs with E minus 1 edges, we know that this is true, right? Because we've assumed that Euler's formula holds for all graphs with E minus 1 edges. This is a graph with E minus 1 edges. So we know that V minus E plus F has to be equal to 2 because of our assumption. And then if we bring that back to the original graph, which has V, E, F versus edges and faces, we know that this must also equal 2. Does that kind of make sense? So we've taken our graph with E edges, we've taken an edge off, so we've got E minus 1 edges now. Then we've applied Euler's formula to see that V minus E plus F is equal to 2, because we've assumed that Euler's formula holds for a graph with E minus 1 edges. So then we know the original graph also satisfies this equation here. Okay. So we've done our base case, done our inductive hypothesis, done our inductive step. We've shown that it's true for case 1 and case 2. So by mathematical induction, Euler's formula holds for all graphs. We've shown it to be true for no edges. We know that if it's true for a graph with e minus 1 edges, then it's true for a graph with e edges. So if a graph with no edges follows Euler's formula, then we know a graph with 1 edge does, and 2 edges, and 3 edges, and 4 edges. So using Steinmetz's theorem, which we covered earlier, we know that if all connected planar graphs follow Euler's formula, then we know that all convex polyhedra will too. Does all make sense? Yeah? Okay. So one more way we can prove Euler's formula is through angles, like we looked at earlier. So Descartes' theorem says that the total angle defect of polyhedron T is 2 pi v minus e plus f, and all convex polyhedra satisfy T equals 4 pi. Can any of you see why that would be true? Yeah.
Isn't it because isn't it because they will be 720 degrees? All convex polyhedra, their T would be 720 degrees, which in radians is 4 pi.
Right. So because we know that all convex polyhedra, we know that v minus e plus f has to be equal to 2, right? So we know that the total angle defect, if we know that that's equal to 2 pi v minus e plus f, then we know that the total angle defect was equal to 2 pi times 2, which is equal to 4 pi. Right? So this here is equal to 2 for all convex polyhedra, so therefore t is equal to 4 pi or 720 degrees for all convex polyhedra. So we can prove the first part of Descartes' theorem. So we can prove that the total angle defect of a polyhedron is always 2 pi v minus e plus f. And then we can use Euler's formula to prove the second part. We can prove Euler's formula from this, but it's much harder. So we're just going to use Euler's formula and Descartes' theorem together. So how can we prove this first part here? I've used the word. Okay. So what we're trying to prove is that total angle defect of a polyhedron is 2 pi v minus e plus f. Minus e plus f, right? So our first step is we can suppose that the polyhedron we're looking at has f faces, and we can label these faces f1, f2, f3, and so on, until we get the f face, because it's f faces, we can call the last face ff. And if we let each of the faces have e of that same number edges, so face f1 has e1 edges, and so on, then can anyone tell me something about what e1 plus e2 plus e3 and so on, until you reach EF. Can anyone tell me what this would be equal to? So we've got F faces, each with E edges. We sum up all of the edges of all of the faces. Can anyone tell me what that would equal? Yeah?
The sum of the faces.
Pardon?
The sum of the faces?
Sum of the faces?
I'm not
What do you mean? What do you mean by the sum of the
Nothing, everybody. You're on.
You're on the right track. So if we count all of the edges on, so for example, if we're counting all of the edges of all of the faces on this cube, we can see that each edge will be counted twice, right? So we count that edge when we're counting the edges on this face, and we count that edge when we're counting the edges on this top face. So each edge we will count twice. So if we the sum of all of the edges of all of the faces is going to equal twice the number of edges in total, because you're counting each of them twice, right? So the total angle defect, this here, T, that equals the total of each of the vertices. So we know that the angle defect is 2 pi minus the sum of the angles at each vertex. So we know that there's V vertices. There'll be V lots of 2 pi in front. Right? So you've got, this is for each of the vertices. We'll sum these up for each of the vertices. So we get 2 pi V at the front, and then we'll minus the sum of the angles at every vertex. Now can anyone tell me what the sum of the angles at every vertex? Can anyone tell me what that would be? What that would be equal to? If we take the sum of all of the angles in all of the vertices.
Of this 3? Or like
The whole cube. If we were to take all of the angles at all of the vertices. Yeah, do you know?
Would it be 270 times by 8? 272 times by 8?
So yeah. So there's yeah, because you've got at each vertex there would be 90 plus 90 plus 90, which is 270. And there's 8 vertices, so that would be 270 times 8. Another way we can work it out is to say that the sum of the angles at each of the vertices is also equal to the sum of the angles in every face. So if we were to find the angles in every face and sum them all up, we'll still get all the angles at all of the vertices. Right? So that's also equal to 360 times 6. So the sum of the angles in each face times the number of faces. So if we use that here, then we get T equals 2 pi V minus E1 minus 2 pi. And we get this from, if we call this is face F, let's say F2, and it has E2 edges, we can say that the sum of the angles in this face here is equal to pi get myself confused. Yeah. Because in degrees we would say the sum of the angles in that shape is 180 plus the number of sides minus 2. Right? Do you all remember doing that? Yeah. So the sum of the angles in a pentagon is equal to 180 times 5 minus 2. So that's where we get our pi is equal to 180 radians, remember? So E1 minus 2 pi, that is the sum of the angles in the face F1. Do you all get that? And then we can keep summing these up, plus E2 minus 2 pi. This is the sum of the angles in the face F2, and so on. I'm running out of space again. And we can, if we sum all of those up, if we sum the sum of the angles in all the faces, if we sum that up, we should get as equal to 2 pi v minus, so if we collect all the minus 2 pi's here, we get minus 2 pi times however many faces there are, right? Because we're doing it for each of the faces. We calculated the sum of the angles in each of the faces. And then also we get E1 plus E2 plus E3 on the side as well. Do we get that? So we get F times minus 2 pi, and then we get E1 plus E2 separately. Oh, and to multiply that by pi as well. And then from here, we said earlier that the sum of all of the edges here, this here, is equal to 2e. Do you remember that? So we get total angle defect is equal to 2 pi v minus 2 pi f, and then plus 2e pi. See where this is going? And then if we factorize 2 pi out, we get v, be careful here, 2 pi minus e and then plus f, right? If we expand this out, plus and then minus it, we get our 2 pi v minus e plus f. So we summed all the angles on all the faces, took that away from 2 pi times the number of vertices, and then we've used our fact from earlier that the sum of all of the edges in all of the faces is equal to twice the number of edges, and then we just simplified. So we got what was that? Does that all make sense? Yeah. Does anyone have any questions?
So how would you cancel out the 2 pi? Because Euler's formula is just the v minus e plus f part. So how does the 2 pi come into that?
So this is the total angle defect. Do you remember?
Yeah.
So total angle defect. Do you remember for the cube it was 720?
Mm-hmm.
So if v minus e plus f is equal to 2, then this is equal to 4 pi. Do we know that's true? So the total angle defect is equal to 2 pi v minus e plus f. And then the reason why all this formula is here is because for all convex polyhedra this will equal 2, right? So we know that for all convex polyhedra the total angle defect is equal to 4 pi. Is that right?
Yeah.
Yeah. Okay. We've got one last bit to go over. So we can use Euler's formula to prove there are only 5 Platonic solids. So the way we're going to do that is we can say, if we call S the number of sides of each of the faces of the Platonic solid, if we call P the number of edges at each vertex, and V, E, and F can just represent the number of vertices, edges, and faces. Can anyone tell me what SF would equal? So that's the number of sides times the number of faces. Any ideas? So the number of sides times the number of faces of the solid. So if we were to count the number of sides on the cube, each face has 4 sides, right? And then how many faces are there? There's 6 faces, right? So SF for a cube is 24. But if we count the number of sides on each of the faces, so if we go here as well, from here, you can see that again we count each edge twice, right? So SF is always equal to twice the number of edges. As you can see, 24 is twice 12, right? If we count all of the sides on all of the faces, we get twice the number of edges. So that's our first equation here, SF equals 2E. Can we all get that? That's basically equivalent to E1 plus E2 plus E blah, 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 equals 2E, right? We're counting all of the edges twice. So right here. And our next equation we can look at is PV. So remember, P is the number of edges at each vertex. So, can anyone tell me what this would equal to? Number of edges at each vertex times the number of vertices? 24 again, right? Number of edges at each vertex, there's 3, right? Here, there's also 3, and so on. So for a cube, it would be 24. But again, if we look at all the vertices and count the number of edges, we'll see that we count each edge twice, right? Because there's each edge connects 2 vertices. So if we count the number of edges at each vertex and times that by the number of vertices, we're counting each edge twice again. So we get our second equation, which is PV is equal to 2E also, right? And now, if we rearrange to find F and V, so that's F equals 2E over S, and V equals 2E over P. If we put that into Euler's formula, I'll write that on the board. If we put that into Euler's formula, so V minus E plus F, so V is equal to 2E over P, E can stay the same, and F is equal to 2E over P. Right? So this here, we know that this is going to be equal to 2, right? If we now, if we take the reciprocal of everything, so right. We can first factorize E out, right? So we get E 2 over P minus 1 plus 2 over, wrong, haven't I? 2 over S here. No, 2 over S here. If we take out 2E here from here, we get that 1 over P minus a half plus 1 over S, right? That is equal to 2. If we divide both sides by 2E, then we get that 1 over P minus a half plus 1 over S is equal to 1 over E. Alright? So just plug that into Euler's formula, then we take 2E out, and then we've divided that on both sides. From here, you can say that 1 over P plus 1 over S is equal to 1 over E plus half, right? And can anybody tell me anything about 1 over E? In terms of its how big it has to be, or how small it has to be? Are there any bounds you can come up on what 1 over E must like to be? If you remember that E is greater than 0, E is an integer greater than 0, what would 1 over E?
So it can't be greater than 1 fraction, but it has to also be greater than 0.
Yeah, right. So 1 over E, it can't quite reach 0, right? Because as E gets larger and larger and larger, it gets closer and closer and closer to 0. And it also can't quite reach, or it can't reach 1, right? Because E equals 1. Give 1 over 1, which is 1. So we know that 1 over E is trapped between 0 and 1, right? So that means that 1 over P plus 1 over S has to be trapped between 1 over E plus a half. So we know that that's trapped between a half and 3 halves, right? So just adding a half to each part of the inequality. Now from here, can anyone see how there are a limited number of P and S that we can choose, right? Because if we were to have 1 over, let's say, 7 and 1 over 3, then this is going to be less than a half, right? So P and S have to be quite small in order for it to be greater than a half. And it turns out the only P and S that we can choose that will work are 3 and 4, 4 and 3. I think it's 3 and 5. 5 and 3. And then the last one, I think, I've got it down here somewhere. Last one is 3, 3. So this one here is our tetrahedron. This here is so P is the number of, what did I say P was? P is the number of edges that meet at each vertex. So 3 edges at each vertex and 4 sides. So that's a cube and 3 cubes at a vertex. Sorry, 3 squares at a vertex gives us our cube. This one here is our octahedron. And these two here will be our dodecahedron, icosahedron, and so on. And that's how we can prove from Euler's formula that there are only 5 Platonic solids. If we tried, let's say 3, 6, if we put 3, 6 into P and S, 1 over 3 plus 1 over 6, that equals a half, so that won't work. So that's why there's no Platonic solid made up of hexagons. And same for 4, 4, a quarter plus a quarter, that equals a half, that won't work. So these are the only 5 Platonic solids that we can get. And if you notice, it doesn't matter which order P and S go, right? Because 1 over P plus 1 over S is the same as 1 over S plus 1 over P. So we can swap these around. You can see this is that swapped around. So these give us our pairs. Do you remember before? When our cube and octahedron were paired, and our dodecahedron and icosahedron were paired, and that can give you some sort of insight as to why they're paired like that. Okay. Thank you for listening.